Welcome to the first in a series of videos that Chris Paola and I have prepared for ESCI 3202. The purpose of these videos is to review some of the underlying concepts that are really essential foundation for dealing with a study of fluid earth dynamics. In the first few videos, we're going to cover really three topics. The first is stress, and this is not the type of stress you feel when you're preparing for your final exams, but rather it's a type of stress important in causing deformation and flow in the earth. It could be, for example, take this block of granite, and if you apply a stress to it, you can change it from a nice undeformed texture to a rock that's clearly been folded and has a significant deformation structure to it. Along with that, we're going to talk about, in the second series of lectures, we're going to talk about the responsive materials strain. And I'd like to really point out at this point that stress is the driver to the system. You apply a stress, and the response function you get is the strain. And we're going to look at strain in all types of materials, including both solids and fluids. Two terms we'll define in our first lecture. And then the third part of this that's very important when you're dealing with fluids is to look at the rate of deformation, often called the strain rate, or the time rate of change of strain, or the rate at which the rock goes from looking like this undeformed granite to looking at like this one that's been heavily folded. So that's where we're going to start, and then we'll move on to other concepts as the course moves along. So the first thing we want to do is look at forces as applied to solids, and we'll go from forces then and eventually talk about how those relate to stresses on the solid. And there are two types of forces that we normally talk about. There are normal forces shown here where you push on the end of the bar, and if you do that, the result will be that the bar becomes a bit shorter. And there are shear forces where you apply a stress to the same surface, but now you apply a shear stress. You apply a shear force along that surface. And the response of the system, if you apply a force, if we apply here an extensional force, then the sample in response gets longer. And if we apply a shear force, rather than changing the length of the sample, we change the shape. And so we take what was a parallelogram or a rectangle and make it a longer rectangle, and we apply a shear force to the sample. We take it from being a rectangle to being a parallelogram. And one thing that's important is that you'll see the forces are always applied in pairs. If I were to apply a single force to this block of granite, I would simply lift it. If I want to stretch it or bend it or fold it, I have to apply two forces opposing each other. Because what I'm interested in this course not is in moving this block of rock around in a rigid fashion, but I want to look at how it flows or how it deforms in response to the applied stress. So we want to take a look now at how the forces are applied to a specific area. So we start out, as shown here, with the end block or the end of this bar that we've been looking at, and we'll expand it out and make it somewhat larger. It has some area A, and there's a force applied, not necessarily normal to or in the plane of the surface. And then we can always then resolve this force into a normal component, that is a component acting normal to the surface, and into a shear component that is a component acting in the plane. And so we see now that the force is a vector. We started out with it pointing up and out of the surface, and that vector can then be resolved into normal and to shear components. And so the important point we want to take away from this is that force is a vector, and what we'll do when we move from vectors or from forces to stresses is we want to think about what is a stress. And we'll see, in fact, that stress is a tensor and not a simple vector. So one thing before we move on is we want to think about that in mechanics problems, such as we deal with in the Earth, we basically talk about stresses rather than forces. In physics, you usually get introduced to forces. Occasionally, you might talk about stresses. But in the Earth, we have a scaling issue to work with, and so we always want to work with stresses. And that point will become clear in a few minutes. So the stress is simply taking the force that we have and dividing it by the area that's the force is operating on. And if we want to look at the normal stress, we'll denote stresses here with the Greek letter sigma. The subscript n stands for normal, and it's simply equal to the normal force component divided by the area in which that force component acts. And the shear stress is very similar. We'll denote it again by sigma, the Greek letter sigma, with a subscript s to symbolize shear. And it's the shear force divided by the same area of that plane. So the areas are the same in the two definitions, but the forces are either the normal force or the shear force. And so the terminology that's often used, and you'll often see in the literature and in many textbooks, is that rather than writing sigma sub s, that shear stress symbol is replaced by the letter tau, the Greek letter tau. And so you'll see those kind of used interchangeably as Chris and I talk about various problems in the earth sciences. Okay, we said before force is a vector, and one thing that's really useful to do before we move on and look at force on a three-dimensional object is just go back to looking at force on our surface and reference that force to a Cartesian set of coordinates. So I've illustrated it, set up a set of coordinates here in the upper corner. And we want to reference our force vector relative to that set of coordinates. And specifically, we want to look at three force components, F sub 1, F sub 2, and F sub 3 that define our vector. And we have the one normal force component, F sub 3. And now our shear force, which was along here in this direction before, now is resolved into two components, a force parallel to the one direction of our Cartesian coordinate system, and a second force, F sub 2, that's parallel to the second Cartesian coordinate. And so we have three forces now, three force components, F1, F2, and F3, referenced to our Cartesian coordinate system, X1, X2, and X3. And to describe forces, particularly when we move to a three-dimensional object, let me clear the annotation since it sits on top of part of what I want to talk about, is that we need to not only talk about this area A, but we need to reference it in terms of the normal to the direction A. And so I'm going to use a unit vector that I've called X3, because it's parallel to the X3 component of our Cartesian coordinate system. And it will define the area that we'll call A3. Rather than just calling it A, we'll now give it a designation A3, again referencing it back to our Cartesian coordinate system. Okay, so those concepts are going to be really important when we start to talk about stress in three dimensions in a few minutes, or actually in the next lecture. So one small point, it's kind of a caveat that's worth saying once. It's not going to be a major issue for what we do, but not all surfaces are flat, as you can see with this illustration of a cylinder, and yet we wanted to be able to define forces or stresses relative to any particular surface. And it's clear that in this case of the cylinder, defining the normal force to the end surface is very simple. It's a flat plane. We don't have to worry about what the orientation of the plane is. But when you look at the surface of the cylinder, it's not flat. It's rotating around. And so I might want to define the force, normal force at this area. And you can see the normal force comes out over to my left, and define the force in this part, and it's off on the right-hand side. And the two vectors are quite different for normal forces. And so the trick that you use is, if you don't have a flat planar surface, is that you define the force rather than in terms of just stress is equal to force divided by area. You take the limit of the force divided by the area as the area tends towards zero, and you get a definition for the stress. But that's a small point, and we'll return to that. You'll see it come up later on. So a quick question. What are the units of stress? What are the units of force? Do you all remember that? And we know their units of area are meters squared. Well, the units of force are newtons. You probably remember that from physics. The units of area are meters squared, and the units of stress are pascals. Okay, so that we'll hear that term used very frequently because we're going to talk about stress, and pascals are simply newtons divided by meters squared. All right, so finally, let's do a quick demonstration about why do we use stress rather than force. And that basically the underlying reason is that often in the earth or in the lab as human beings, we work with rocks that are about that size, and I might take that to my lab, put it in a high pressure, high temperature furnace, and squeeze on it and cause it to change shape. If I push real hard, maybe I can get it to look like this. But I want to apply this knowledge that I get, and it could be applied to the flow of magmas or the flow of water or the flow of rocks, such as in this case. I want to be able to apply this sort of basic idea not only to lab scale or human scale samples, but I'd like to apply it to larger scale objects. And one kind of obvious situation would be in mountain building. I want to know how much stress do I have to apply to this piece of granite in order to cause it to deform and upwell and make a mountain type of formation. So here's a photomicrograph or photograph of a piece of granite that comes from University of Indiana's website. Granite similar to this, although it has a bit more K feldspar in it, potassium feldspar in it. And that's a scale of maybe 1/10 of a meter, maybe even a little bit smaller than that. And I want to go from understanding something at that scale to understanding something at the scale here of Mount Rushmore, which is made up of Harney Peak granite. How did you get, if I understand the strength of this rock at this scale, can I begin to understand the strength of the rock at the scale here of 100 meters, or it could be at the scale of 100 kilometers in the earth as I go through mountain building processes. So the idea of using stress is that if I talk about the force to deform this, if I were lucky, I could break this or deform this rock with my hands. I could never push up the Harney Peak granite by hand. I'd need a larger stress, a larger force to do it. And I want to be able to go from the lab scale to the earth scale, and therefore it's really fundamental to talk about stresses rather than forces. And finally, I was going to give you one quick demonstration of this idea. I brought along 2 pieces of copper, one here between 2 brass rods that I will momentarily pull on and hopefully deform, and a brass rod, which is essentially the same material, roughly the same length. And I'm going to pull on this and deform it, and if I'm not successful, I'm going to bring it to class and ask you to deform it. But let's start out with the copper wire, which is relatively small diameter. It's maybe less than 1 millimeter in diameter. And if I measure it, here's my measuring tool. It's about 30 centimeters in length. And let's see if I can make it at least a little bit longer. It may break at the end of this, but if I pull, I'm sure you can see how quickly this is gating. Always breaks, but nonetheless, I've managed to lengthen it by a few centimeters by pulling on it. And now, of course, I can take this rod and pull, and as hard as I pull, which is pretty hard, this rod will not get any longer. And the difference is they're the same material, they have the same fundamental strengths, but because of the size, I need much greater force to deform this material, but I would need exactly the same stress to deform this large rod as I did to deform this fine wire. So the important point of this sort of demonstration is that stress really is the critical factor. If we want to understand how to take what we learn in the lab and apply it to what goes on in the earth, we need to use stresses rather than forces. And stresses, again, are simply forces normalized by the cross-sectional area. And it's a way of saying that size of the object that we're trying to deal with really does matter. And so we want to get to a fundamental material property, that is the strength or the stress required to deform it. And you're going to see this discussion of scaling permeate throughout much of what we talk about this semester. It applies to rates. Rates that we apply in the lab are typically something that has a time scale of a day, whereas in the Earth has millions of years to accomplish the same thing. So scaling in time and in space, from small objects to large objects, from short times to long times, is really a fundamental problem in the earth sciences, and you'll see it reappear as the course goes on.